All right, good morning, everybody. Welcome back from exam land. Hopefully that all went smoothly. Let's see, where did we kind of end off here? We talked about last week, we talked about, we started chapter 4, which was about electrons and light. And if I just kind of check back here where we did finish off. All right, so we were talking about how waves can interact and how electrons kind of behave. So let's go ahead and start with there. Alrighty, so we'll talk about more about electrons today. And so, without going too much into the physics of it all, when the waves that kind of describe how electrons move, when they kind of combine or cancel each other out, we're going to see that we end up with a number of shapes. And these shapes can be kind of, we can make an analogy between what are called standing waves and what we're going to see is going to be our orbitals. If you were to tie a string between kind of 2 points, if you just tie a string there, and you were to oscillate it, that means move it up and down really quickly, you'll see at certain speeds, all you will see is something that looks like this. This is just called a standing wave. And we're going to see here that, like, kind of this distance here would be half its wavelength. Because it's taking essentially kind of that whole distance to go just the top part, and then the whole distance to go the bottom part of the wave. Remember, waves have top parts and bottom parts. So that would be kind of just half the wavelength, the distance there. You don't need to know that. But what we work with these things, though, is... hold on. I think we're a little bit off to the side. There we go. Now you can see wave. Okay. This one's kind of not so interesting. If we go ahead and double our kind of speed that we're moving this kind of string up and down, we're going to see we end up with, we capture essentially an entire wave within our string. And so now this is an entire wavelength that goes here. And what's important that we kind of understand here is that there is going to be a point at which the wave has canceled itself out. There's a point where it's 0. We kind of ignore the points at the ends. We're just looking kind of at stuff in the middle here. And we're going to see that these kind of standing waves will also match the ways that our orbitals, that the electrons are occupying, will kind of occupy, or will shape. These will determine their shape. If we keep on going, if we keep increasing the speed that we're oscillating this wave, we can now have 2 nodes. Those are all nodes. And so this exercise, or this kind of idea of comparing it to standing waves, where we've tied a string to 2 points and are moving it up and down, the point of this is just to show us visually how waves might interact together. And since electrons sometimes behave like light, they behave as both like light and particles. It's an interesting kind of duality there. Because they have characteristics of waves, we're going to see that there's a point to this, is that the quantum chemists, or physicists, it's kind of a bridge of both, have kind of come up with equations to describe the motions of electrons. So, hold on, the motion of electrons. Because we know electrons are constantly zipping around the nucleus, right? They're moving very, very quickly, the speed of light, pretty much. And so they're just zipping around there. And it's important that we kind of understand how they're moving, so we can kind of predict where they'll be. And we're going to see that this power of prediction will kind of allow us to do a lot with the chemistry of things. And so kind of this is our very basic introduction to quantum chemistry. This is as far as it goes. We talk about these equations as wave functions. In math, a function is what we might think of as a standard equation, y equals something in terms of x, right? That's just a normal equation for a graph or a line or a parabola or whatever. Those are functions, right? And specifically, we call these equations that describe electrons wave functions because they behave like waves. And so we're going to see that the orbitals that these functions predict, if we were to graph these wave functions, we get a couple of shapes out. If we take a look at that first one here, we call this one n equals 1. It's actually kind of a bad letter to use for this, but okay, I'll use it anyway. We actually call them as L. Okay, fine, I'll use the right letter. These letters you don't need to know as well. We describe these as L. It's a letter that we're going to deal with next semester if you keep on taking chemistry. But suffice it to say that if you're looking at these things, they're going to predict a shape when the scientists have kind of compiled these wave functions and kind of figured out the probability of where an electron might be at a given time. And so for L equals 0, that's our first one. I'm just using these letters to correlate between these. So our very first drawing where we have no nodes, we get what is called an s orbital. It is spherical. So, terrible at drawing 3D, but suffice it to say it is a spherical orbital. So the electrons that occupy this orbital are going to be moving in a spherical pattern. So they're going to be moving all around, and they're free to go kind of wherever they want. And that's what we get out of the waves that describe s-orbital electrons. If we move to the next one, we get what are called p orbitals. And they look like little dumbbells. What's important, though, is with these dumbbells, we have a node there. And just like the waves above, the node is where those waves are completely canceled out, right? They don't exist at the nodes. We see that with electrons can never exist at the node either. So we're going to see that the electrons can kind of occupy either side of the node, but they actually never pass through it, which is a little bit bizarre for us to think of. Well, how do you go from that top part to the bottom part without ever crossing through the middle? Don't worry, electrons are somehow able to do it, right? There's your typical science fiction answer, right? Is quantum, right? Classical physics, physics that we may understand about the real world around us, does not apply to electrons. That's why we have quantum physics, because they're so small that they do things that we would not be able to understand. So, like if I wanted to go across the room here, I would have to somehow teleport through my desk, right? Like this desk is forming a node. I can't go through the desk. But electrons, and I can't get to the other side because I'm not an electron. But an electron would say, aha, your desk, you're in my way. Well, that's okay. I'll just magically teleport to the other side. And so electrons are capable of doing this. Perhaps not magically, but using their own laws of physics. What's interesting, though, is with the spherical orbitals, we just kind of have one because it is just a sphere. We're going to see, though, with the p orbitals, we can actually have different orientations of them. We're going to see that we can have p orbitals that are completely horizontal, and then ones that are kind of going in and out. And then we have three different orientations here. So depending on which direction these are moving, they have three different orientations. So one's up and down, one is side and side, and the other is kind of in and out. So I'm kind of drawing that one kind of diagonally, but that's the one that goes in and out. So we have, X, Y, and Z directions. So that's how those can be oriented. If we keep on going, we're going to see that there are more shapes that we can occupy. This is a d orbital. At one point, I didn't know where these letters came from, by the way, but I do not remember at all anymore. I know the S came from spherical, but the PD and what we'll see are F, I do not remember where those comes from. And if we look at the d orbitals, notice we had two nodes in our standing wave. We're indeed going to have two nodes here. So we have a node going here. So we have a node there. So electrons now have kind of four lobes in which to dance around and do electron things. And so those can be occupied by the electrons, and again, they can't cross those nodes. We're going to see with these d orbitals, there are going to be 5 orientations that we can make. I'm not going to draw them all. You don't need to worry about them, but suffice it to say there's going to be some that are in line with the the regular XY Z plane or graph. Some are going to be a little bit out, and we have one little weird one that looks like a little it looks like a p orbital with a donut around it. There's one d orbital looks like this, and again, these are just mathematical predictions. So there's one that looks kind of like that, which is pretty interesting. So the other 4 look like that like flowery thing above that just rotated in different ways. In fact, it may be a little bit easier. Sterling, shush. D orbitals. I could show you pictures of them that are much better than things I can draw. If we switch over to Google real quick. So d orbitals, if you look here, again, they're these 4-lobed things that either are in the XYZ planes, or they are kind of just rotated throughout. And then there's that fun one in the middle that's got the p orbital with a donut around it. And so we're going to see here that all of these still have the kind of the 2 nodes idea. And so that's kind of what they look like. The last one I cannot possibly draw But here are your f orbitals at the bottom. So you've got now 6 little lobes. So these look more and more like flowers, right? Sometimes you have 8. Sometimes you've got this double donut thing going on. You don't need to know these shapes. I'm just showing you kind of how these shapes look. Mostly we focus on S and P because those are going to be where most of our chemistry is going to be taking place. F orbitals, honestly, I have no idea what they do. This is like, these orbitals you'll find in like uranium, things that we don't typically think about doing chemistry with. And so they're a bit more complex. And as you can see here, you know, the f orbitals, while I have not written them out, their L equals 3 would be their, what we call quantum number. You don't need to know that either, don't worry. But these are what the orbitals look like. So these are just mathematical representations of these wave functions that scientists have come up with to describe how electrons move. All right, so I'm going to just write out, these would be f orbitals, and there are 7 of those. 7 kind of combinations. So f orbitals, let's see. So there's 1 f orbital. Again, don't worry about learning the shapes of those. So, but that's what f orbitals, what 1 f orbital looks like. You saw that there's a couple that have various different things. So, cool. So those are our orbitals. And we're going to see that those orbitals, we're going to be able to kind of predict which electrons are going to occupy which orbitals. And that's going to be kind of the big part about this chapter, is how do we know which orbitals are occupied by which electrons. So, as we go into this, there's a couple of things we're going to need to kind of accept before we can start talking about this. The first one is that each orbital can hold 2 electrons. And the other thing that we kind of need to also understand is that electrons prefer to be as low energy as possible. Everything in chemistry wants to be low energy. That is why things react. They react to lower their energy. And so, with that, as we kind of understand these things, I have a couple of patterns for us. We're going to see that in general, an s orbital will have the lowest energy, and f orbitals have the highest energy. So, in general, if we were to compare some orbitals, an s orbital has lower energy than the other 3 types. A d orbital has less energy than f, but more energy than p or s. So, this is a pattern we have. Ouch. And we're going to see we have another number that... Sorry, this is being a little wonky. Okay. We have another number which describes the shell. of our Sterling shush. That helps describe these electrons as well. So these orbital types are called subshells. These are called subshells. And so they are kind of all within what we used to describe the electron or the atom as. Remember when if we go back to that Bohr model? Do you remember this, like where we have just the orbits around the nucleus? These bits we would call shells. So each kind of like general circle we call shells. These orbital types, though, are called subshells. So each shell has a certain number of subshells, depending on how big it is. But suffice it to say, though, these shells that get progressively uglier and uglier the more I draw them, we can see one simple pattern, though. And that pattern is that the bigger your shell is, the farther you are from the nucleus. And that means it's higher energy. Electrons like to be close to the nucleus. And so by having them in bigger shells, ones that are farther from the nucleus, they're a little less happy. They're a little higher energy. And so we can describe all of these things. So in general also, actually this is not in general, this is a absolute statement. Your shell number will also correlate with your energy. So your lower shell, wherever is closer to the nucleus, is smaller. And so we see that this will be lower energy, and this will be high energy. So we've got two patterns here. We've got shells, which are these kind of overarching ones, and then we have the subshells within those shells. So the subshells all combine to make up the shell. And, sorry, I'm a little bit, just too high. So the subshells are those ones. We have our shells here in the middle. And so we're going to be able to compare them. How we might compare orbitals for lack of a better way of describing it, NL, where N is your shell number, and the L is your kind of orbital, we'll say letter, but really that's orbital shape. So SPDF, those are what L represents. And so we could say something like a 4s orbital. So it is an S subshell located within the fourth shell. We could say something like a 4p orbital. That is the p orbital contained within the fourth shell. And if we're to compare these energies, if we want to compare two orbitals and say, okay, which one is higher energy, which one is lower energy, I'm super red today. Usually I'm blue. I guess this camera is red focusing today. Who knows? We're going to see that the s orbital is lower energy than the p orbital. we have our pattern here. In general, we're looking at the shell numbers as well. The shell numbers were the same for these. So we can just instead look at the subshells. And we'll say, aha, yes, that's right. S is lower energy than P is. So the 4s orbital should be lower energy than 4p. If we want to compare, say, these two, we can do that as well. If we want to identify which one is higher energy, well, we'd want to compare. We'd say, okay, we got 4D and 2S. If we kind of look up here, okay, well, we know that D is higher energy than S. Oh, and 4 is also higher energy than 2. So this one should in fact be like way higher energy than the 2s one. So we have higher energy in the 4d orbital. So comparing them is not too bad. Things get a little tricky when we're saying something like this, where we know d orbitals are higher energy than p orbitals, but the fourth shell is higher energy than the third one. And so this is not obvious. And I would, at this point, not expect you to know the answer. In this case, the answer is that the 3D is the lower one. But that don't kind of just assume that's always the case. So in this case, that's the pattern here. We're going to learn how to figure this out when we have kind of comparisons to make. But we have one more thing to talk about before we start comparing the energies of more orbitals. All right. Do we have any kind of questions so far on this? So far? The fun part is we're spending all this time just kind of setting the foundation for the part that is really going to be useful for us. And so this stuff may not make super sense to you, but that's okay. There's going to be something that we are going to take away from this that I'm hoping will make more sense. This stuff, I'm okay if it's just kind of in your brain going like, oh, okay, yeah, we vaguely talked about that. Kind of just setting the stage for what we're going to really talk about here. So, let's go ahead and do our last little bit here. We're going to see that there are 7 total shells. And each of them is going to be made up of certain subshells. And thankfully there's a nice pattern here. We're going to see that the first shell only has the S subshell. When we get into the second shell, we have 2 subshells. The third one, guess what? Has 3. And then all the rest of them have 4. So we only have 4 letters, right? So once we have reached 4, Then the rest are just going to be continuing on. Alrighty, so far, these are the subshells we have that make up those corresponding shells. Just out of curiosity, there is something special about the number 7 in regards to chemistry, in that our dearest friend, the periodic table, has, well, I guess not anymore, but had, we'll say, 7 periods, right? Helium is the first one. This is our first period, first row of the table, second, third, fourth, fifth, sixth, 7 rows of the periodic table. Those do correspond with the shells. All right. I guess I'll say the rows, the periodic table. So the periods, the horizontal bits there. And we're going to see the whole point of this is going to help, or our periodic table is going to help a lot with understanding this idea. Okay, is there anything else I wanted to go on before we started talking about these? Alright. So, again, here we have generally speaking, we have our lower energy ones up top and our higher energy ones on the bottom. And we're going to say that we're going to go to a concert. Things that COVID has deprived us of. Maybe we shouldn't go to a concert with the Delta, but we're going to go anyway because we're chemists. So here we go. Concert time. Okay, here we go. There's our concert. Someone is going to be singing for us. All right, questions for us then. If we have our choice of seats at this concert, well, let's just say we've got kind of some choices here. And then we've got kind of some more seating back here. Then we've got maybe the lawn back here. And then maybe we've got some more seating back here. Here's our concert. If all these seats cost the same, where would you like to sit? Ideally, probably towards the front, right? And I'm going to describe us as little arrows. Makes sense. Oh my gosh, that's not even the closest one. Shame on me. So, there happens to be a second seat in this front area, and so the second person to buy a concert ticket is probably going to want to sit there as well. Right? Why not? If they're the, same price if all the seats are the same price, you're going to choose the closest ones. And we're going to see that, as people keep buying tickets, we might start just getting farther and farther away from the stage as we keep buying more and more tickets. Now, what's interesting is, as humans, we do not like to be with other people. And so the next person to buy a ticket might be like, okay, I'm going to go here. The fifth person to buy the ticket. And then the sixth person might be like, well, I'm going to sit over here. I don't want to be in a place that has other people. And the next person, maybe here. And then unfortunately now, okay, well now we've got to start actually filling the rest of these. So now it's like, oh, darn. We have to pair up. Make some more. And we're going to see that this kind of pattern is going to be holding true as we start talking about these electrons. We're going to see that this is akin to the nucleus, the stage. This is going to be our 1s orbital, our 2s orbital, and our 2p orbital. And had we continued, we would have some more orbitals to deal with. Remember that the S subshell is spherical, and it's got only kind of one iteration of itself. Remember those p orbitals, though, we could actually orient them in different ways, right? If I scroll all the way back to those p orbitals, remember we had 3 different orientations we could make with the p orbitals. And so we actually have 3 distinct p orbitals. Though we often refer to the p subshell as one thing, there are 3 individual orbitals within that. And so we're going to see that's why we have 3 boxes here, essentially. And we're going to see that these corresponded with our elements. We're going to see how this looks. So, here we go. Let's get to it. When we describe the electrons of a particular element, we're going to see that, say, for hydrogen, it has 1 electron, normally. That electron can go wherever it wants, and electrons will always choose the lowest energy places to be. And so, with that, we're going to see that of all those options available to us, I'm going to just draw the same ones I drew for a little concert here. Of all of these, the hydrogen's electron is going to go for the lowest energy one. So of the ones that I've drawn here, we have the lowest energy on the left, the highest energy on the right. So the electron, which is represented by a kind of little arrow there, will occupy the lowest orbital. And that's what hydrogen will do. And so we describe this as, if we were to look at the electrons of hydrogen, we would say that hydrogen has 1 electron, and it's got it in the 1s orbital. So we'll say the name of our orbital, our subshell, and how many electrons are in it. So hydrogen has got 1s1. So it has 1 electron, and that electron is located in the 1s orbital. Little, not very exciting, but I'm going to actually copy this. If we look at helium, which has 2 electrons, Helium, which has 2 electrons, Remember, each orbital can hold 2 electrons. And so those electrons are going to want to occupy the lowest places before moving on to the next one. And so we usually draw this one upside down to account for something called spin. This is something we'll talk about in 111, but electrons can't be spinning the same direction. It is just a rule of nature, and so we usually draw one with up spin and the other with down spin. That's not something you need to worry about. Just put them one up, one down. That's what you want to do. So it's got 2 electrons. We know that because its atomic number is 2. And so, I'm sorry, not 2s2. We would describe the electron configuration of helium as 1s2. It has 2 electrons in the 1s orbital. If we go ahead to lithium now, which has 3 electrons, so I'm just going from left to right on the periodic table. Oh, why did I do this? I have this copied. I've already got our 1 electron in there, but we've got 3 electrons now. And so we're going to fill those in. So we always fill up our lower boxes first before we start moving to the next one. And so if we want to describe lithium's electrons, we would say, well, it's got 2 electrons in 1s and 1 electron in 2s. Go away, CM Knuckles 151. You are not welcome here. Someone remind me to fix my spam filter to get rid of, I'll put big follows specifically on, the do not allow list. So, remind me to do that. I'll take care of that. Oh, what is this? The P's have been cut off. Okay. So, that's our lithium. I'm going to skip beryllium because it's the same old business. Let's skip over to boron. Boron has 5 electrons. And so if we fill those, we're going to always fill our boxes up within the subshell we're looking at until the next one, we'll see. If we were to write out its configuration, we would say, it's got 1s2, 2s2, 2p1. That's what's called the electron configuration of boron. The other thing next we need to worry about is, with this 2p business, if we look at carbon, which has got 6 electrons, and we take our boxes here, we can put the first 5 in, no problem. But now we have to decide, do we pair that off, or do we move to the next box of the P? And we are going to indeed fill the next box before we start pairing them off. This will become very important when we talk about unpaired electrons next semester. So we're going to see things that have unpaired electrons can do different things. Often they're magnetized as well. So not to say carbon's magnetic, carbon does different things, but we'll deal with that later. If we still write this out, though, the configuration would be 1s2, 2s2, 2p2. We don't need to distinguish that the electrons are in different boxes in the P because of a new fancy vocabulary word, are degenerate. And that just means equal energy to each other. So if we wanted to be super accurate about this, if we're just looking at the p, maybe this is 2p, we saw that those p orbitals could be arranged in different directions. One could be along the x-axis, the y-axis, or the z-axis. And all of those are equal energy to each other. So here's our py. This is our px, and then we have our pz, which is going in and out. All of those are equal energy to each other. And so electrons would rather be by themselves first. Since they're equal energy, we can put them into separate boxes. And we can pair them off later. So because we draw these as degenerate, same energy as each other, all three different p orbitals within the 2p subshell have equal energy, we will separate our electrons first. So we want to kind of half fill our orbitals before we start pairing them off. That's the point of this here. So we will kind of place electrons separately into degenerate orbitals. Degenerate, again, meaning basically anything that's not s. So p, d, and f all have degenerate orbitals. So if we look at oxygen, let's see this in practice again. Oxygen has got 8 electrons. Again, on the periodic table, if you find oxygen, it's got an atomic number of 8. So if we're looking at the element oxygen, it's got 8 electrons. And so if we are to fill these in, we'll have our first 2, number 3, number 4, number 5, number 6, number 7, number 8. So notice how 6 and 7 went into their own boxes, and then I started pairing them off within 2p. I still will describe this using this sum of them. I'm going to say 2p4. There are 4 electrons within 2p. But we're going to see here that they had been separate, and now we're starting to pair them off again. And so this pattern just keeps on going. So the more electrons you have, you're just going to have to fill more and more and more as we go through. But we have shortcuts. Shortcuts that are going to make this a lot easier for when we're figuring out the electron configuration of something with 35 electrons. You know, it's a little bit hard to draw out all these boxes and start filling them and counting things, and it's going to be a little tough. But notice a couple things here. All those s orbitals, for whichever subshell they're part of, they can each hold 2 electrons. And we see that the p subshell can hold 6 electrons because there's 3 orbitals that make it up. Let's write this all out, by the way. We're going to see that an s subshell, the letter s, any of these s orbitals, 1s, 2s, 3s, whatever shell it happens to be part of, can hold 2 electrons. And we see that. They can hold 2 electrons each. If we look at the p subshells, those can hold 6 electrons because there's only one s orbital within the s subshell. It's just the one sphere. There's no way to kind of orient those spheres so that they don't overlap, so there's only one. There are 3 different p orbitals. Each of them can hold 2 electrons, so overall we can hold 6 electrons within the p subshell. Remember, those 3 orbitals are just the different arrangement of those in space. So we have one that's up and down, one that's side to side, and then one that's in and out. Those were the 3 different p orbitals. With d orbitals, we see we're going to have 5 of those. We looked at their pictures earlier. And since each one can hold 2, the d subshell will hold 10 electrons. And then if we go to f, we're going to hold 14. So notice that the orbital number increases by 2 each time, and therefore the electron capacity increases by 4 each time. All right. So we have some interesting things to do on the periodic table. Some patterns that we're going to pick up. Some interesting patterns here. Within these 2 kind of sets of columns, what do we notice about the number of columns in each? Well, if we count them up, we have 2 columns there on the left. We have 6 columns there on the right. How interesting. That seems to correspond with the numbers we have of S and P subshells. And if we count here, I don't really have numbers for these. We don't really use numbers with these, but notice how many columns we have in that middle block. Interesting. So altogether, by the way, I put the group numbers instead of counting them, but overall that's 6 columns there. We have 2 columns with the green numbers. We have 10 columns with the purple, 6 columns with the blue. And while I didn't write it out here, notice we have 14 columns in the thing down there. I'm not going to write them all out, but we have 14 of those. So notice those numbers all correspond with the capacity of each orbital subshell. And so we have names for these things. We call that block on the periodic table, excluding helium, the P block. And we're going to see patterns. Here we have the S block. Here we have the D block. And then finally down there, I guess I used black, that is our F block. And we're going to see these blocks correspond with the highest energy orbitals that something is going to occupy. I will write that down. the blocks on the periodic table correspond with the subshell of highest energy for an element. So for example, if we go ahead and look at, what did we do for this one? We did boron. Notice 2p, 2p, where's oxygen? 2p. They all had 2p as their last orbital. That's the highest energy one. And notice boron, carbon, oxygen. All of those fit on the periodic table in the p block. And here, I'm going to in fact erase these numbers. And I'm going to redraw them in blue. Notice also that boron was in the first column of the p block, carbon was in the second column of the p block, and oxygen is in the fourth column of the p block. And if we look at those things again, oh, boron 2p1, and boron was in the first column. Carbon 2p2, carbon in the second column. Oxygen 2p4, oxygen's in the fourth column. Interesting. All of these in the periodic table will tell us kind of the last bit of our electron configuration. So if we were to guess for something like chlorine, I'm going to also write on here, by the way, something like chlorine, I'm going to have to erase P block for a second, but here's chlorine. What's nice for us is we see, well, chlorine is in the third row of the periodic table. It's in the P block, and it's in the fifth column of the P block, from left to right. We saw that all those elements in the second row, boron, carbon, oxygen, those are the ones we looked at. Boron was 2p1. 2p1. And that's where boron was. Oxygen, 2p4. Because that's where oxygen lined up. So, chlorine, therefore, should be 3. I've erased the P5. And indeed, it is. So if you were to write out chlorines with its 17 electrons, if you were to fill those all up, you'd see, indeed, you would end up with 3p5 as your last electrons. Whatever. If you were to do this for chlorine, I'm going to do it one last time. This business. 17 electrons. Here we go. We've got one already in there. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So, notice we have 5 electrons in 3p as our last bit. And notice also that everything that was lower energy is completely filled. To its maximum capacity. And so, once we know the last electrons, the highest energy ones, we know that it also has every other lower energy electron orbitals filled. And so once we identify the end one, we just have to have everything else completely filled, and we'll have generated our electron configuration. If we were to write this all out, by the way, 1s2, 2s2, 2p6, 3s2, and then we have our 3p5. So, if we can identify its highest electrons, everything else has to be completely filled before it. And we have nice ways of figuring that out as well. On the periodic table, I'm going to draw it again. It's 3s there. All of these correspond S block on the left, period of the periodic table, which row, which block. With the P block, it's the same. Remember, we don't have a 1p. 1p does not exist because the first shell only has an S. So helium is technically also 1s. That's why it's by itself there. And so that's why I excluded it from the P block. Oops, I'm totally out of space. So, there we have it. I've now put the orbitals with their shell. And so we can see here, chlorine that was right here in 3p5, well, we know we have to fill every orbital that comes before it in energy. And we saw that we went all the way from 1s to 3s for things that are filled. And notice that before 3p, if we were to just, let's use purple. If we were to kind of just keep going along the periodic table, we have gone through 1s, we have gone through 2s, through 2p, through 3s, through 3p, ending at 3p5. So we've filled every orbital that comes before it, and we can get those orbitals from the periodic table. So instead of having to do these boxes each time, we can just say, okay, well, I know I'm 3p5. What comes before 3p? Oh, well, that's 3s. I just look at the periodic table. And then before 3s was 2p. So remember, like you have sodium here and neon here. Neon is 10 electrons, sodium is 11. So sodium comes after neon. So we just keep going left to right on the periodic table. I'm going to erase those two elements. We don't need them here right now. Oh, I've ruined my periodic table. And so, if you can look on the periodic table, you'll be able to see your final electrons. So remember chlorine, we found it because it was in the third row, in the P block, in the fifth column of the P block. So therefore it was 3p5 was its last electrons. And to fill everything else before it, we just look at the periodic table and be like, okay, well, we know we've filled 1s. Starting at hydrogen, just keep on going. We start with 1s, we filled it. Start then 2s, 2p, 3s, and end at 3p. I'll show you another way that a lot of students prefer to use, but the periodic table will never lead you wrong. All right, notice if we were to keep going, say do calcium, well, it's right here. Calcium's right there. Notice calcium is in 4s, fourth row of the periodic table, S block, second column of the S block. So we are expecting calcium's highest energy electrons to be 4s. And it's the second one, so 4s2. So calcium was there. If you want to fill in everything before it, we can work backwards. We can say, okay, we start with hydrogen, so we fill our 1s orbital. We remember s orbitals hold 2 electrons. After 1s, we then go to 2s, fill that one. Next is 2p, as we are just going along. So now we're at 2p. Fill that up, except it's 2p6 because p holds 6 electrons. Remember, everything before your last electrons is completely filled. After 2p, we keep on going on our periodic table. We hit 3s, fill that one up completely. Then we go to 3p, fill that one up completely, and then we're at 4s2. And that's our electron configuration. We're going to see why this is important probably on next week, but coming up with these electron configurations is super, super important for when we talk about how these things are reacting. Notice, though, something's a little strange here. What happened to our 3d orbital? Remember that scrolling up. Oh my heavens, look at all we've done today. We saw, oh wait, in the third shell we should have a 3D subshell. Where did that end up going? Why did we go to 4s next? Well, suffice it to say, remember we kind of did that comparison. We know that this is the D block here. That's the D block in the middle. The transition metals occupy the D block. We're going to see that the first row of the D block is actually where that 3D will end up. So our D subshell is actually, in terms of energy, it's going to be, our 3D subshell is in between 4s, so it's higher energy than 4s, but lower energy than 4p. And so we see that 3D is in between those two. So we have 4s, 4p. Our 3D energy, D orbitals have higher energy than either p or s, right, of the same shell. But if we're comparing different shells, we see that the D orbitals will fit in between the s and p of the next higher shell. So that's why these numbers here are actually one less than their row is on the periodic table. So the 3D subshell is actually in the fourth period. This is in between because that's the energy. We don't start filling the D block until after 4s. That's the way the energy works out. And so we just need to remember that everything in the D block is one less than it should be. So as we're filling things, we're going to cross through the D block, and we're going to have to fill it as we go through. And we will fill it after 4s, but before 4p. So because the 3D subshell is higher energy than 4s, 4s gets filled first. And so if we're looking at the periodic table, as long as we understand that the D block has one less number than it should for the row that it's in, we can still use the periodic table to fill things out. So if we say we look at, selenium. Selenium on the periodic table. Let's go ahead and look at that. Selenium. Let's go and find it on the periodic table. Well, in fact, let me see. I think I should be able to write on this somehow. Aha, there we go. Screen right, there we go. I think it copies it and then I can write on it. So, selenium, no, go away. So selenium, here. We would say that selenium would be 4p4 is its last electrons. And so we need to fill everything up until 4p4. So we'll go through hydrogen. That's 1s2. We go through 2s. We go through 2p. Fill that up completely. So remember, p's take 6. We go through 3s. We go through 3p. Then we go through 4s. And now we go through 3d. Remember, d orbital holds 10 electrons. And then we end up with our 4p4. So we just have to fill everything up on the periodic table. And understand that the D shell that we go through, even though it's in the 4th row, is only 3D. So D orbitals are always one less than their row. And so we end up putting that in between the two. All right, so I'll leave it on this screen for a second so we can see all this fun stuff I did with it. So I just went through the rows on the periodic table until I got to selenium, filling the orbitals as I went, by understanding the blocks of the periodic table as well as the rows. So S and P use the same number as the row. D uses one less. And we'll see later F uses two less, but that's something we'll talk about much later on. All right, so we saw that we had, I'm going to just copy it down. We were able to find 4p4, and then we have to fill everything else before it. Or if you really want, you can bust out your boxes and start doing that, but you're going to have this 3D problem. So, without the periodic table, what's a way for us to remember this? I have one for you. a way to remember, or a way to tell you which is higher energy, all that stuff. Sterling is here. That's an unusual. He doesn't usually bug me during class time. Here he is. Hi, buddy. Hi, Sterling. He just wants me to feed him. So he's usually doing other things, but he came to say hi today. So, okay. Here's our cheat sheet. Oh no, I don't have enough space. Okay, there we go. So a cheat sheet, but a mnemonic device. So a way to help remember. So if you don't want to use the periodic table, if that method doesn't work for you, which it might not, if you copy this, we're going to see that understanding the number of orbitals that we have of each type, or all the subshells, sorry, will tell us how to do it. And how this works is we are going to just draw diagonal arrows down this thing. And we're going to see that we cross through arrows as we go through. So I'm going to take that one back up to the top. We're just going diagonally through things. And we follow these in order. So this tells us, as we go through 1s, that's our first one to fill. Then we go up, back up to the next arrow, now that we've finished it, and that arrow goes through 2s. And then we go back up to the top again, and now we are going through 2p and 3s. Oops. And then we go back up to the top, because we've reached the end of our arrow, so we go back up to the top. I'm going to erase that bit. We then go through, as we're following this arrow down, we go through 3p and 4s. Go back up to the top. Now we go through 3d, 4p, 5s. I'm just going to list them all in their energy. 5s. Now we go back up. Next is 4d, 5p, 6s. So notice how we're just following these arrows down. And all I did was just draw these arrows diagonally through. After 6s, we go back up to the top to our next line, which puts us through 4f, 5d, 6p, 7s, and then if we just keep going, 7p, 6f, well, I mean, really, 7p is kind of where we end. So we don't really have to worry about those last ones, because 7p will put us at element 118, which is our highest known element. So these are the order. This is the order of orbitals. Same on the periodic table, but a lot of students like this way, this mnemonic. And so you'll probably find better drawings of it online if you just like Google electron configuration thing. I don't know. I don't know what you'd Google, but you'd end up finding this mnemonic. It's pretty common. It's in the textbook as well. But periodic table is always your friend as well. So either of these can work. And so once we identify our orbital, like we did with selenium, we saw it was 4p. Everything before it needs to be filled completely. So if we were to do that, I need the eraser, that's why. So for our selenium, we saw that the selenium was, notice that the order is the same here. We saw that selenium was 4p4. So we just have to fill up everything completely. So S's get 2s, P's get 6, D's get 10, F's get 14, if we had any, and we will end up with our unfilled orbital at the end here. Ah, look at how much we've done. One little shortcut we can do as well. Well, it is important that we can somehow or talk about electrons in this way, seeing all of them at once. Sometimes it's a little bit less relevant because we're going to see that only electrons in the very kind of outermost, highest energy orbitals are going to be doing the chemistry. So we can kind of shortcut our lower energy orbitals. And if we draw our periodic table, did I forget one? 1, 2, 3, 4, 5, 6, 7. Okay, there we go. Notice the noble gases have full orbitals. Like helium would end up with helium special, right? It's just 1s2. But neon corresponds with having 2p6 filled. All of these have their p orbitals filled otherwise. And so we can represent everything up until a p orbital as a noble gas. So if we take a look at selenium again, I should have copied the one with the numbers, but I'll write them out again. What we can do is find our kind of biggest p orbital that's filled and say, oh, well, that's really just argon. And so we can just say, well, this configuration would be argon's configuration. And then we're going to add out our extra other stuff. So we can kind of use a shortcut and be like, well, we know argon is everything up until 3p, everything filled. And so we can say, okay, well, let's just say argon's configuration plus the rest of the stuff. The reason we could do this is, I'm going a little bit ahead of stuff here, but really only s and p electrons do chemistry for us. Chemistry, I think I wrote there, but that's good enough. Chemistry. And so understanding like that higher energy orbitals do chemistry, and really it's only s and p. These, what we call core electrons, they're pretty much unreactive for any element. We're going to see that anything that's not S and P and not the highest shell really don't do anything. So we can go ahead and just hide those in these noble gas configurations. And how you'll do these noble gas configurations is you'll find your element. You'll look on the row before it on the periodic table. So selenium is right here. We saw, okay, well, the noble gas right before it, the one on the row above, is argon. So we're going to use argon and then just worry about the stuff on the periodic table. Then we can worry about 4s, 3d, and 4p once we already have argon done. So that's why it's a little bit easier to use the periodic table, even though this whole thing may be easier for you. For the noble gas shortcut, you pretty much have to use the periodic table. So once you figure out which noble gas you have, you can just set that as your kind of like base configuration, and then add on everything else that's not argon. So that would be 4s, 3d, and 4p. So everything after argon you'd need to fill. If we're looking at, say, iodine, iodine is here. It is in the 5th column of the 5th row in the p block, so 5p5. If we look at the noble gas before iodine, it's krypton. So if we're looking at iodine, we saw the noble gas before it was krypton. And we know its last electrons were 5p5. So we're only missing a little bit of our configuration. We have most of it now. Krypton takes us all the way through 4p6. So we don't need to worry about that. If you want, you could say, okay, well, we know krypton will take us through 4p. So I just need 5s, 4d, 5p. I could use this thing, but I prefer using the periodic table. So 5s, 4d. Going through krypton, after krypton is 5s, so we're going to go through that 5s. We're going to go through the 4d, and then through the 5p as well, up until 5p5. And so we just need to write that out. So we'll have 5s and 4d. Those were the two we're missing, and we're going to want to fill those completely. So we've got our electron configuration now. Quite a bit easier to use the noble gas configuration. Little shortcut here. Which is our shortcut. So, we are out of time today. We will continue this on Thursday, and we'll go from there. All right, so that's it for today. We'll continue talking about this stuff next time. I'll put up a homework for you guys so you can start working on it if you like, on electron configuration. All right? Sounds good, everyone. Take care.